Thanks, Joe. Well, I'd like to thank the organizers for inviting me and for specifying the topics that I should be talking on. I'm glad they didn't pick cohomology of pre-sheaves or something, because that would be a real challenge. So what I'd like to do in this first talk today is to describe an area that's a natural intersection between geometry and combinatorics of the classical sort. And it's called Euclidean Ramsey Theory. So in order to talk about it, let me just give you two sentences. What is Ramsey theory? Well, subject in combinatorics, which has kind of various descriptions. You might describe it as the study of unavoidable regularity in large structures. And we'll see many examples of this as we go along. You know, kind of theorem zero is the pigeonhole principle, but it hardly even counts. It's been described very succinctly by the late Ted Motzkin with the statement, complete disorder is impossible. And actually, if you saw A Beautiful Mind, you'll see John Nash pointing up, looking at patterns in the stars, saying, well, look, you can find this, you can find that, because you have a lot of stars, and so there's certain unavoidable regularity there. Well, okay. The crux of this, or one of the founding theorems, but actually not the first theorem, is Ramsey's theorem itself. And let me just state it once. It's true, I think, in this branch of combinatorics, that the statements you have to read 2 or 3 times because they have kind of a large number of alternating quantifiers for all there exists, or they're all for. So what this says is that for any k less than L and any R is typically a number of colors, there exists some large number, typically capital R, the Ramsey number, so that no matter how you R color the k element subsets of a capital R element set, you can find some larger L element set so that all of its k element sets have the same color. And typically you see this applied when k is equal to 2. And then the 2 element subsets of a set you can think of as edges on a graph on, say, capital R points. And you're looking for complete subgraphs. So all the edges, complete L element subgraphs, so all the edges have the same color. Now, because you'd go nuts trying to repeat all these quantifiers, I might say, who was Ramsey? Ramsey was a very interesting guy, actually. Here's a picture. Oops. There's a picture. Frank Ramsey. Probably not as well known as his brother, who was Archbishop Ramsey, the Archbishop of Canterbury. And in fact, Ramsey's widow, who lived in Cambridge all her life, was a photographer and died not so many years ago. And say within the past 10 years, came upon a box that had actual reprints of Ramsey's paper. At that time, nobody cared about it much, and so she wrote to some of the local mathematicians saying, does anybody want one of these reprints anymore? And he kind of spread them out. So I have one somewhere, carefully put away, but of course I can't find it, but at least I know I have it. Okay, good. So what is Euclidean Ramsey theory? Well, Euclidean Ramsey theory is applying this philosophy in a geometric setting, in particular in Euclidean space, although at the end, as Barry Mazur said, gee, you could do this in hyperbolic space too. Well, I suppose nobody ever did it. But anyway, here's the setting. You have now some finite set X in some Euclidean space, and you have congruence of X, the family of all subsets X prime, which are congruent to X up to some Euclidean motion. Now, there are various restricted families for which you can apply this theory. You could just do translations or homotheties or whatever, but now these are just congruents. You're not even allowed to flip it over. And you'll say a set is Ramsey if, for all R, number of colors, there exists some n, now a dimension, so that no matter how you partition the points in Euclidean n space into R classes, R colors, if you will, one of these classes contains an X prime which is congruent to X. So again, it just says, and we'll see a number of examples of these Ramsey sets, It just says you have a finite set of points. It's Ramsey if, for any number of colors, I can find a large enough dimension so that when all the points in that dimension space are split into R classes, or given one of R colors, you'll find in a single color a copy of X. And this is abbreviated typically by this arrow notation that Erdős and Rado popularized, just says that E, capital N, arrows with R colors, the set X. Okay, so we'll see that a little bit. Well, there's a nice compactness principle which says that if Euclidean n space actually arrows X, then there must be a finite subset of it already which arrows it. So if you're looking to show that a set is Ramsey, you don't have to look for all possible colorings of all Euclidean space. All you have to find is some finite subset. So that, and it turns out the compactness principle needs the axiom of choice. And at the very end of the talk, a paper that just came out within the past month by Schella and Seufer shows that one of the classic problems now, so-called chromatic number of the plane, which we'll get to at the end, everybody believes it's, well, it's at least 5 maybe. If you change the axiom of set theory slightly, the answer changes. So we'll see about that. It's slightly ominous. Okay, well, let's start with something easy example. Here's a 2-point set, X, separated by distance 1. And of course, the actual distance doesn't really matter here, but say you have 2 points, distance 1. So X has 2 elements, and the claim is that's a Ramsey set. Why? Well, given the number of colors R, I'll take for my finite set YR just the R plus 1 vertices of a unit simplex in Euclidean R space. Okay? And it's clear that if you R color these points, 2 of them must have the same color, and they have distance 1, and that's what you wanted. So it's easy to see why R. Okay, good. Let's look at a little more interesting set, and it'll give you an idea of some of the techniques that you use to prove that sets are Ramsey sets, and also give you an idea as to why some of the bounds get large. So now our finite set, Q sub n, denotes the set of 2 to the n vertices of the n cube. And you can write these as just all the 0, 1 vectors of length n. And the claim is that's a Ramsey set. Special case was 2 points, distance 1. I mean, that's kind of a 1 cube. Well, here's a theorem. It says for any k and any r, there's some large number, capital N, so that any R coloring of already not Euclidean n space, but just a large cube, an n-dimensional cube, must contain a monochromatic copy of, well, not quite the k cube. The k cube scaled up by a factor of square root of 2. That's just, I could put the square root of 2 over on the other side, but it's just notational simplicity. We'll get a slightly bigger. You could scale everything down if you really want a unit cube. Doesn't really matter. Okay, well, what's the proof? Here's the idea of the proof. Induction, of course, on k. And for k equals 1, well, the 1 cube, we kind of just did that case, right? And we're going to choose n1r to be r plus 1. And these are our r plus 1 points. In fact, these are the vertices of a unit simplex of side square root of 2. And as we've already seen, if we only use R colors, then some pair must have the same color, say these pair, this pair, and this is a monochromatic one-dimensional cube, side square root of 2. Okay, good. So far, so good. Now, we didn't really make a lot of progress here. Okay, k equals 2. I'm going to tell you the n to choose. For n2r, choose r to the r plus 1 plus r plus 1. So we'll call the first piece n2 and the second piece n1. And what we're going to do is look at not all of the whole n cube of that dimension, but I'm just going to look at n2 times n1 points. These are all points whose n1 plus n2 coordinates. And the first n2 have a single one, and the second n1 points have a single one someplace. So you can think of it, there's a single one in the first n2 and a single one in here, n1, n2 points. And if you look now arranging it this way so that the first n1 points have their n2 coordinate 1 in the first coordinate, then there's kind of a little diagonal matrix. There's kind of a small simplex right here. And you can associate to that, we often call it a fat point. So with this single point here, there's kind of another n1 points hanging onto it there. And you can do the same thing over here. So you have this picture and so forth. And so each one of these n2 points represented by this can be colored in at most r to the n1 ways, because you can pick r colors for the first point here, and r and r and r. So the original r coloring of this cube, and therefore these n1 times n2 points, induces an r to the n1 coloring of q n2. And in fact, just those n2 points. But the way we chose n2 was equal to r to the n1 plus 1. Some pair must have the same coloring, because there are just slightly too many pairs to have all distinct colorings. And so you'll find 2 points like this where these big chunks are colored in the same way. But now these are monochromatic by the choice of n1, and so that means all 4 of these are monochromatic. And I claim these 4 points from a monochromatic square of side square root of 2, because here are the 4 points represented that way, and it's just a matter of checking that, well, okay, we can check. You can see that the distance between any 2 of them is exactly square root of, well, it's not you have to check that, it actually is a square. The distance between these 2 is square root of 2, and between one on the top and one on the bottom is actually 2. So it is your square, and so forth. And you can see n3 is equal to, you can be defined to be this way, and it's one of these recursive inductive constructions. And continuing in this way, the theorem is proved. This is called proof by, not intimidation. As Helmholtz once said, it's not to really prove it, but to induce the benevolent feeling of credulity. That's notice, though, the bounds get kind of large this way, because you're kind of taking exponentials in whatever the previous number was. It shows, for example, n42 is at most 2 to the 27th plus 13 by this bound, but I'm sure it's much, much less. I think it's 6 or 7, something like that. What's the true order of growth? I don't know, but this is nothing compared to what's coming. Okay, good. So using this technique, you can prove something called the product theorem. It says if you have 2 sets that are Ramsey sets, then the Cartesian product is also Ramsey. After all, the cube is just the Cartesian product of 2-point sets. And in particular, any subset of a Ramsey set is Ramsey, and therefore any subset of the vertices of an n-dimensional rectangular parallelepiped is Ramsey, because a rectangular parallelepiped is just the product of 2-point sets with different distances. So for example, any acute triangle is Ramsey, because any acute triangle is a subset of vertices of an n-dimensional, in fact, it doesn't have to be n-dimensional, 3-dimensional rectangular parallelepiped. So the question is, what about triangles like that? They do not occur as subsets of vertices of rectangular parallelepiped. Well, how do you get obtuse Ramsey triangles? Well, here's an example. And it's kind of illustrative of another new technique. If you choose n to be this Ramsey number, 7, 9r, remember what that means? It means it's a number so large that if you r-color all the 7-element subsets, you'll get a 9-element subset, so all its 7-element subsets have the same color, okay? And I'm going to look at a certain finite set of points in Euclidean n space. These are points that have all coordinates 0 except 7 of the coordinates. And the 7 coordinates in order, the non-zero values, are 1, 2, 3, 4, 3, 2, 1. So for example, here's such a point. So you see it's 0 every place except the first non-zero is a 1, and then later you come to a 2, and then later a 3 and a 4 and a 3 and a 2 and a 1. So you get all these points in here. It's some finite set. And there are n choose 7 sets points because, for any, that's where the 7 non-zero coordinates might be. Okay. Now any R coloring of this set will induce an R coloring of the 7 element subsets of 1 to n. Namely, the color of this point is the color of the corresponding subset where the non-zero entries are. Well, okay, that's great because that's what we need for this Ramsey number up here. And by the choice of n, which was this Ramsey number, there must be some 9 element subset of indices with all its 7 sets having the same color. So here is a 9 set of indices. Okay, so that's, if you look at the corresponding point here, then, okay, what are its 7 element subsets? Well, the first 7 corresponds to a point 1, 2, 3, 4, 3, 2, 1. And you could also, here's another 7 element subset. There are a lot of different 7 element subsets up here. I'm picking these 3. And by our choice, they all have the same color. And if you look at the distance, between A and B, it's root 8. B and C, it's root 8. And A and C, it's root 26. And so this says that this particular triangle, which if you check is actually an obtuse triangle, is a Ramsey triangle. Okay, well, now what? Well, same technique will show that actually you get square root of 2t, square root of 2t, square root of 8t minus 6. Where there's 1, 2, 3, 4, 3, 2, 1, you just have to have a longer thing there. And the angle between the short sides of that triangle gets as close to 180 degrees as you like. It's almost a 1, 1, 2 triangle. Well, now if you form the product with some other interval, then you know that this whole 6-point set is a Ramsey set. And now this triangle between A, C, and B prime is also a Ramsey triangle. And now you can control the angle exactly just by adjusting this side. So this shows, it's a theorem of Frankel and Rödel, all triangles are actually Ramsey. And I'll give a little bit about the history in a minute. In fact, they showed in 1990, if you take any non-degenerate simplex, not only is it Ramsey, but its Ramsey number, that is, there is some constant, so that if you R color the points in Euclidean C times log R space, you'll get a monochromatic copy of this simplex. Non-degenerate means it spans a positive volume. But what about something like a regular pentagon? And that really stopped us for a while. Well, it turns out that Igor Krzys in 91 has a very kind of the strongest theorem of this type so far. If you have a subset that has a group of isometries which is transitive and solvable, then your set is a Ramsey set. And so this particular shows that any regular n-gon is a Ramsey set. And he extended that a little bit to show that, in fact, if it just has a solvable subgroup with at most 2 orbits, and the group of isometries is transitive, then it's also Ramsey. So the Platonic solids, the dodecahedron, icosahedron, those sets are Ramsey sets too. And you might ask at this point, are there any maybe it would be a nice theorem. All sets, all finite sets are Ramsey. Well, nope. Here's a set that's not Ramsey set. The 1, 1, 2 triangle. You wouldn't think of it. 3 collinear points, distance 1. That's not Ramsey. And kind of following the axiom that every mathematics talk should have at least one, or is it at most one, proof, here's the one-page proof. This is not a Ramsey set. So what I have to do is, for any number of colors, here's the proof, I'm going to actually 4-color all the points in Euclidean n space. For any n, I'm going to 4-color it to avoid 3 collinear points distance 1. So I claim there is a way to 4-color all the points Euclidean n space and never get this 1, 1, 2 triangle. Well, how am I going to do that? Well, we're going to take the point x. We're going to take the square, this is the inner product, the square of the distance from the origin, round it down to the next integer, and reduce that modulo 4. So that's an integer that's 0, 1, 2, or 3. That's the color. So every point gets color 0, 1, 2, or 3 by this recipe. Take the square of the distance, round it down, reduce it mod 4. Well, what does that coloring look like? Well, if you think about it, you know, around the origin there's a little sphere that's radius, well, I guess 1, right? And then you get shells as you get further out, this thinner and thinner shells. So these are kind of spherical shells that get very thin as you get out there. But you might think you ought to be able to, you know, to get really thin, you might be able to slide this thing in here, get 3 collinear points. Well, okay, so let's look at a copy of this 1, 1, 2 triangle. So here's x, y, z sitting someplace. Here is your origin, and here's distance 1, and there's some angle theta here. So actually, this lies in a plane. It's just sitting out there in n dimensions. And if you look at the law of cosines in this triangle right here, then a squared is b squared plus 1 minus 2bc, 2b cosine theta. Good to remember those things. And the other triangle over here for c squared, in this triangle here, and the natural instinct is to add these together because you'd sure like to get rid of this theta that we don't know anything about. And so here's a squared plus c squared is 2b squared plus 2. And this kind of expresses the fact that these 3 points are collinear. Actually, is what's that saying. Okay, now, suppose x, y, and z actually had the same color by this spherical shell coloring. Well, what would have to be true? Well, a squared would have to be, I mean, if it has some color d, then how did it get color d? Well, a squared, which is the distance from the origin of this point x bar, must have some fractional part that's strictly less than 1. And so you reduced it, and then you reduce mod 4, and you're left over with d. So a squared must have this form. 4 times an integer plus d. D is 0, 1, 2, 3, plus some fractional part. And the same is true for b squared and c squared. Okay, good. Well, we have an equation, star up here, that these things have to satisfy. So let's plug them in. If you do that, you'll get this equation here. There's epsilons. And now we ought to collect all the multiples of 4 together. So here's 4 times all the multiples of 4. The 2 d's cancel, and there's a 2 left over. So 4m minus 2 is equal to this expression in epsilons. But you just can't quite get to either minus 2 or 2 with these epsilons. Just barely. You can't get there. Because the epsilons are strictly less than 1 and greater than or equal to 0. And this is impossible. So it barely works, but that's okay. Barely is okay. In fact, you can call a subset X spherical if it's a subset of some sphere. And this is the dimension, d-dimensional sphere, radius rho. And kind of the culmination of this argument led to the following result. If you do have a set that's Ramsey, it must be spherical. Any set that's a Ramsey set must lie on the surface of some sphere in some dimension. And you see 3 collinear points don't. So that's, here's the only known picture, not too good, of the 6 authors here. This is Joel. You probably know Joel. Bruce is down at UCLA. Here's Paul, who's reading the good book, but we'll talk about that a little later. Here's Peter Montgomery, who's right now up at Microsoft. Very interesting, nonlinear kind of guy. This was taken actually, I think, in Poland. Here's Ernst Strauss. I don't know how many people here knew Ernst Strauss. He was at UCLA. You know, one of the things that Erdős liked to kind of talk about was co-authors, because he had a bundle, like more than anybody. And the question, who has the most distinguished co-author? Well, Strauss always won, because he wrote 2 papers with Einstein. He was actually Einstein's assistant at the Institute for a few years, and but he was a very interesting guy. Well, as a corollary, any 3 collinear points, distance a and b, are not Ramsey. In fact, you can 16 color any Euclidean n space and avoid any a plus b triangle. I don't know if 16 is best possible. Maybe 4 is best possible. Maybe 2. I just don't know. For a while, it turns out that the early form of this theorem, if the ratio of A to B was irrational, then 16 would do the job. If it was rational, then the number of colors depended upon the rational number. But we got over that. Now 16 will do it, but maybe 4 is even better. Now you might call a set sphere Ramsey if for all number of colors there's some dimension n and some radius, so that all partitions of the points of a sphere, n-dimensional sphere of radius rho, into R classes, one of these classes contains a copy of X. I mean, somehow Ramsey sets are spherical, so maybe you ought to just take the points of the surface of a sphere and just see what's true about that. And note that if a set is sphere Ramsey, then it's Ramsey, and if it's Ramsey, it's spherical, because every Ramsey set is spherical. So, well, Matusek and Rödl show the following very nice theorem, that if you have a subset of a unit d-dimensional sphere, finite set, then for all R, number of colors, and every positive epsilon, there's some n, so that the points of an n-dimensional sphere of radius 1 plus epsilon actually arrows X. So if you take a slightly larger sphere of a high enough dimension, you R-color it, you must get a copy of this. And the question, of course, then X is sphere Ramsey, that's the definition. The question is, do you really need this epsilon? I mean, after all, your set is a subset of a sphere of radius 1, so maybe higher dimensional spheres of radii 1, one of those would also have, well, yeah, you really need the epsilon. And there's a result not so many years ago that says if you have a set which is unit sphere Ramsey, that is, you can always R-color the points of a large dimensional unit sphere, then you have some constraints. Any linear dependence of these points must imply a non-empty subset of these coefficients whose sum is also 0. And if you think about this for a little bit, that if your set has 0 in its convex hull, then it can't be a unit sphere Ramsey set. So you really need this little epsilon. So there are a lot of directions here, and I just thought I'd give you a flavor. In fact, this whole talk is kind of giving you the flavor of this particular subject, which is, I think, what these first few weeks' talks are supposed to do. Now, suppose you fix the dimension of your space. What's true in this case? Well, the thing we've been doing so far is whatever your set is, number of colors, then the dimension gets larger. But suppose I say I'm going to fix the dimension of the space. Well, here's the simplest set, again, 2 points, unit distance. You can define the chromatic number of the plane to be the least number of colors R, so that for some coloring of all the points in the plane, no one of these color classes has 2 points at unit distance. So again, you're trying to color the points in the plane so that no unit distance occurs monochromatically. How many colors do you need to achieve that? Well, what's the value? It's been open about 60 years. The best bounds are between 4 and 7, which were known on the second day, or maybe the first day that this conjecture kind of came up. In fact, whose conjecture is this, you see? It was kind of floating around. Erdős kind of talked about it, but he said, it's not mine. Is it Hadwiger? Is it Moser? Is it so forth? It actually seems to be due to Ed Nelson, who's at Princeton, and he was a grad student in Chicago at the time, and sent letters to people, and people liked it, and he knew between 4 and 7 already. There's a guy named Alexander Seufer at Colorado who publishes a journal that probably not too many people read, called Combinatorics. And it's kind of the journal of Euclidean Ramsey Theory in some sense. No, he focuses a lot on this problem. And so here's the Moser's graph. I'll say where the name came from in a minute. This is 7 points in the plane, and these line segments are meant to be unit distances. And this has the property that if you 3-color these points, you must have 2 points that have the same color unit distance apart. You can just check. It's actually occurred in papers of Leo Moser. This is Leo. This is with Erdős. But Leo has a brother. Leo Moser died some years ago. In fact, there's a very nice story that he was writing a book and had a contract with a publisher. And the publisher, of course, the book, like a lot of books, kept getting delayed, and the publisher was getting anxious. And he said, look, it's really going to be a nice book. Everybody's waiting for it. Tell me honestly, when do you think this book is going to appear? And Leo said, well, honestly, it'll probably be published posthumously. And the publisher said, well, okay, but let's make it soon, because we really So that's the publishers, okay. Here's Erdős with Willie Moser. Willie's up at McGill, was the president of the Canadian Math Society, and in fact, Willie has 2 manuscripts of his brother Leo, which have many problems in geometry and other unsolved problems that he was always going to write up and publish, but it never happened, of course. So, pardon?
He still talks about this.
Okay, well, encourage him. Encourage him. Let's make it soon. So this shows in particular chromatic number of the plane is at least 4. Here's one of the standard 7 colorings of the plane, where each of these hexagons, a hexagonal tessellation, has diameter 0.9. So you can't have 2 points in one of these that has the unit distance, but 2 that have the same color are a little too far apart. So, and there it is between 7 and 9. Now, kind of recent progress was made. Well, I'll mention that in a minute, but what about Euclidean 3 space, you see? Well, it's now known between 6 and 15. Same question, 6 and 15. And this is all fairly new. 2000, the value of 6, and then much more recently, Radojcic and Gabor Fejes Toth, I think, is it? Oh, no, different Toth. Geza, yeah, Geza, right. Probably, do you think they're related way back someplace? I don't know. Well, anyway, between 6 and 15, and I still think there's probably room to improve that. In Euclidean n space, it's known to grow exponentially between about 6/5 to the n and 3 to the n. In fact, for a long time, this is a result of Frankel, Rödel, maybe it comes out of Wilson. It was only known to be polynomial lower bound, but it's, it's definitely exponential. There's a result that not so many people know, to O'Donnell, that shows this. You see, the Moser's graph has a triangle in it, and so that has girth 3. He showed that for every G, there's a 4-chromatic graph, which is what the Moser's graph, it takes at least 4 colors, unit distance, so the edges are unit distance in the plane, whose girth is larger than G. So already to find one whose girth is 5, I mean, because it's a pretty sloppy thing, and yet you can't 3-color the vertices. And so maybe this is evidence that supports the conjecture this is at least 5. I don't know. I mean, $1,000 problem. Determine this. Now, this is following the tradition of Erdős. It actually followed an earlier tradition. If you read the famous Scottish Cafe in the problem book, where people offered a bottle of wine and this and that, and Erdős made it a little more quantitative offering, although he often would change it. Well, it should be a Japanese yen or Deutschmark or something, whatever is the best currency. Determine the value. And we'll see more about some of these problems. A little set theory. Most of us are working in ZFC, which is Zermelo-Frankel axioms to get the axiom of choice. I mean, that's what we use, the compactness result and so forth. Now, here's our familiar axiom of choice that just says any family of non-empty sets has some choice function. Okay. Now, there's a weaker function called DC. I don't know if DC is weaker than AC. Anyway, that's what the logicians call it. The principle of dependent choices, and this just, I'll just state it, but I'm not going to, there'll be no test on this at the end. So if you have a binary relation on an unempty set, then for every A here, there's some B related to A, and for every A such that there is a B, there's some sequence, A1 up to AN, so that the sequence is related. So I guess I'll have to take the logician's word for it that this is a weaker form. But another useful axiom in set theory that isn't part of the normal equipment, but logicians like to throw it in there, LM. Every subset of real numbers is Lebesgue measurable. And that's that's an axiom that you can use or not use. And Solovay showed if you assume the existence of an inaccessible cardinal, which we're not going to be talking about too much today, then the axioms of Zermelo-Frankel, together with dependent choices and LM, is still a consistent theory. That's just a somewhat different theory. And result that just came out very recently of Shelah and Seufer, if you assume that any finite unit distance graph in the plane has chromatic number at most 4, then in ZFC, the chromatic number of the plane is 4. We saw that because if it's 4, then there must be a finite set that's 4. But in this slightly modified system, the chromatic number of the plane has to be 5, 6, or 7. And so the conclusion is this might help explain why people aren't making progress on this problem. Maybe we have the wrong axioms. Now, in fact, there's a whole small industry, I won't say it's a large industry, it's called reverse mathematics. And this is an area within logic where people say, look, this is a theorem we'd like to prove. What are the axioms we need just barely to prove that? You know? And Harvey Friedman has been pushing this a lot, trying to develop theorems that are kind of, quote, natural combinatorial theorems where you can prove you need the existence of n malo cardinals. And various large cardinals, you need to know they exist to prove it. I mean, it's an example of Gödel incompleteness. There are theorems that are true in your system, but you can't prove them in the system. You have to extend ZFC in order to prove these theorems. And the whole issue, how natural are these theorems? A little bit like Paris-Harrington and things of that type. In fact, only at a higher level. Well, okay, enough of that. What are the beginnings? Some of the beginnings of this Euclidean Ramsey theory was an observation by Esther Klein. If you take any set of 5 points in the plane in general position, that is, no 3 collinear, they must contain the vertices of a convex foregone, convex quadrilateral. Well, you can do that. It's one of the few results that Erdős would actually prove in a talk, because you can just draw one picture. And in general, if you let f of n denote the least integer, so that any set x of f of n points in the plane in general position must contain the vertices of a convex n-gon, you could define such a function, but the question is, does it exist? And if it does exist, how do you determine it or estimate it? And there's a long story that Sekerish wrote about this. I'll give you a little history in a minute. Where she actually picked up Esther Klein in the 20s, was going to Göttingen and kind of picked it up, or at least was stimulated by it, brought it back to Hungary, and so forth. And Erdős and Sekerish then published on the problem in 1934, showed that it always exists, and in fact, it lies between 2 to the n minus 2 plus 1 and 2n minus 4 over n minus 2 plus 1. And so this bound is about the square of that bound. And in doing this, they actually rediscovered Ramsey's theorem, which wasn't known to them at that time. And this is a very seminal paper in which they did this. In fact, Neshatrul and I wrote a paper on all the kind of implications that came out of this particular paper. And as I say, they gave several proofs that it existed. And Erdős often called this the happy end theorem, because George Sekerish and Esther Klein were married shortly thereafter that. And in fact, here they were in 1927 and 1928. Here they are 10 years ago. And in fact, I went to Sekerish's 90th birthday celebration about a little over 2 years ago in Australia, still doing fine, as is Esther. In fact, Esther published her first joint paper with Erdős about 5 years ago. Of course, Erdős died 7 years ago. So, that was the current status of the problem. And in going, here's Erdős and Sekerish at Erdős's 80th birthday party. And Erdős died in 96. And in going over to one of the memorial ceremonies, we thought that it would be nice to at least improve the bounds. That problem's been open since 1934. Try to improve the bounds a little bit, you know. So we worked pretty hard and made an improvement. Well, it took a new idea. You had to have a new idea to at least get +1 down there. We hope that this is a small hole in the dam that now water starts rushing through, and pretty soon, sure enough, Kleitman and Pachter got it down by a linear factor, and then, oh, here's a picture of Kleitman, and here's Bruce. Here's actually Katana's son, who's now a mathematician. Here's Katana. I don't know if any, it's so long ago that he didn't have hair. I mean, now he does. But anyway, that's another story. Okay. And then I guess Geza, Toth, and Walter now improved the top part of the binomial coefficient to 2n minus 5. So this is about half as large. So they cut the bound still by half. But still, the upper and lower bound differ by about a square. And so there's a conjecture, which I gladly offer 1,000, to prove that it's actually equal to that number. Now, this is tight in that it is possible to produce a set of 2 to the n minus 2 points, in general position, so there's no convex n-gon. And, but you might think, well, it should be pretty easy. Because, look, it's obvious, right? I mean, you increase the dimension, you double the set, you do something. No, there's no easy construction. In fact, the first description of this in the Erdős-Ekerich paper was sufficiently unclear that they published another paper many years later kind of clarifying, or at least filling in some of the details. And if you look at this construction, this power of 2 turns out to be the sum of a whole bunch of binomial coefficients, which is in some sense kind of an accident that they just happen to be such a nice number. This is only known for n up to, let's see, I think already at 17, it's not known that 17 points forces a convex 6-gon. There's a variation of this, which I didn't write here. Suppose you not only want a convex n-gon, you want it empty in the sense you don't want any of the other points inside that set. So now, how large must your set be to guarantee that you'll have a convex n-gon and none of the other points are inside of it? You know, it might be a little skinny thing. It turns out you get the numbers up through 5, and for n at 7 and beyond, doesn't exist. There are sets as large as you like, so that every convex 7-gon has a point inside. 6, still open. Nobody knows whether it's finite or infinite, but that's a side remark. Now, more beginnings, and this is kind of very typical of Ramsey-type theorem. You might say, is it geometrical? Well, to the extent that arithmetic progressions are. Van der Waerden's theorem from 1927 says in any partition of the integers, now in the finitely many classes, say R classes, one of these classes must contain k arithmetic progressions, k-term arithmetic progressions for all k, arbitrarily long arithmetic progressions. And a lot of people have looked at this theorem. In fact, Van Waerden even wrote a paper on how he kind of got, how the proof finally came out. It was, and Artin and Schreier were both kind of involved in some sense. Here's Van der Waerden, who died, at a ripe old age. In fact, when I was a student at Berkeley, he actually was visiting and gave a course in algebra. Wasn't a great lecture, but it's a good course. Okay, these are k-term APs. And Erdős and Turon already asked in 1936, okay, it's nice that some class contains arithmetic progressions of length k. Which class is it? Well, it's the biggest one somehow, whatever that means. So here's Erdős about that time. In fact, one of Erdős's teenage friends lives pretty close to here. His name is Andy Vazony. He lives over in near Sonoma State. And he's there, and he actually, Fan Chung and I wrote a little book on Erdős's graph theory problems, and he put 2 chapters, what it was like to know Erdős as a teenager. I mean, Erdős was a little nerdy in a way. I mean, he was very focused on that, but it's an interesting story. Anyway, interesting story. So what Erdős and Turon conjectured is if your class is dense enough, in some sense, then this should imply that it already has k-term arithmetic progressions. And looking at it kind of in the other way, if R sub k of n is the least integer, so that any subset of 1 to n with at least rk of n elements in it must contain a k-term AP, then you'd like to estimate this rk of n. That is, what's the smallest number of elements from 1 to n so that if you take any set with that many elements, you must have a 3-term arithmetic progression, or a k-term progression. And they conjectured that this was little o n. That is, you don't have to take any positive fraction to any k. Well, progress was slow, although Barron in 1946 showed that R3 of n was already larger than n times e to the minus constant root log n. And what you should take from that, that's bigger than n to the 1 minus epsilon for any fixed epsilon. So definitely if rk of n is going to be little o n, it's not going to be little o of n to the 0.999. It goes bigger than that, you see. So it's going to barely make it if it's going to be true. Roth showed, in fact, R3 of n was big O of n to the log n of the c. This was one of the results cited in his Fields Medal citation. So this particular R3 of n used analytic techniques. Semredy in '69 showed that R4 of n was little o n, and that was a big step there. Erdős, about that time, offered his first $1,000 problem for rk of n, little o n. Semredy was starting a family, $1,000 is a lot of money, highly motivated, and he did show that rk of n was little o n for rk. And what Semredy got was $1,000, and what the world got was the regularity lemma. So those of you in combinatorics, there's something called the regularity lemma of Semredy, very powerful tool, and that was the first occurrence developed for this. And it's often the case. You work on a hard problem, and you may or may not solve it, but to solve it, you often have to create new tools. So that's what Wiles was doing, for example, in Fermat. See, did people really care about Fermat? Well, but the tools he created to actually attack it now have a lot of application. Here's Semredy about that time. Actually, the version that Semredy wrote kind of sketches, and nobody could understand it. So I said, look, I want to really understand it. So I took out a few months and wrote it all down in a giant, careful way. And that was the version that was published, actually. I never saw the galley proofs. It was just to be sent to people who were in the field who wanted to know what was going on. So I put a flow chart at the beginning showing this lemma implies that. It fills up the whole page. And at the bottom it says proof of Semredy's theorem. Now Semredy would never write that, but that actually appeared in the journal. So it was, but here's a little story that was in Science. Erdős, hard to win prizes, still draws bounty hunters. Here's one of the signed but unfilled in checks that Erdős left just in case. There's still a lot of problems. Of course, if you solve one of his open problems, say $100 or $500, where do you go to collect? Well, you could wait, collect later. But actually, the ones in graph theory we published in the book, I'll pay. The book's been out, I think, 4 or 5 years now. So far, no one's submitted a claim yet. Although it says, when this came out, 2002, Erdős still published 62 new papers in the past 5 years. So he's slowed down, but the old saying, death is nature's way of telling you to slow down. Well, he slowed down, but okay. Anyway, then R3 of n, Heath Brown and Semredy made improvements showing that this was even a better upper bound, and Bourgain even has a somewhat better. But the big news, Gowers 98 showed that R4 of n was big O of n to a power of log n, and that was cited already in his Fields Medal citation. And people knew the general case was floating around. It wasn't quite ready yet, but now it's accelerating. And Gowers showed in 2000, although the paper was, he really took great pains to try to explain what was going on. It's about 135 pages, but he shows why some of the approaches you might try if you know how to do 4 don't work for 5. So he's really trying to make it friendly. And he showed that rk of n got this quantitative bound. I might say Semredy's proof doesn't give any quantitative estimate. It just says a little o n. And in fact, shortly after Semredy in '74, Furstenberg and Katz-Nelson and quite a few people using kind of ergodic theory were able to come up with a different proof. In fact, that approach seems to be a little bit more powerful, at least than just this pure combinatorial approach. Although now Gowers is using analytic techniques and quasi-randomness and Feynman's theorem and kind of a lot of, you get more tools, you might get more done. Now, one of the implications here, kind of the quantitative version, the finite version of van der Waarden, says the following. If W of n is the least integer, which is guaranteed by van der Waarden's theorem, so that every two coloring of the first W integers has an n-term arithmetic progression in one color, the question is, estimate it, and that's been open for a long time. Van der Waarden's proof was a double induction, and so the bound he got was not even primitive recursive. It grew like the Ackermann function. Shelah, about 12, 14 years ago, actually got it down to the fifth level of the Gregorczyk hierarchy, because it's not just a tower, but a tower of towers of, it's just almost a tower. Gowers, though, as a corollary, showed that W of n is less than 2 to the 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 n plus 9 for all n. Well, already, it can't be such a simple proof to give that kind of a bound, but I had offered $1,000 to show that it was less than a tower of 2s of height n. This definitely did that. So it cost me $1,000. I kind of hoped it was tax deductible as a professional expense, but well, it's okay. So, there I actually paid off at a meeting in Hungary. It's good. I try to write these checks suitable for framing, And unfortunately, people seem to cash them. Okay, and then they want to cancel checks back. Right? But undaunted, there's another conjecture that I believe that actually W of n should be less than 2 to the n squared for every n. I think that's even a very generous upper bound. Actually, it's much... Pardon? So the best lower bound is due to Berlekamp, who was here at Berkeley. 1968, he took off a weekend one day from his algebraic coding theory and showed using the finite fields that W of n plus 1 is at least n times 2 to the n. So basically, it's growing lower bound exponential. I think 2 to the n squared should be an upper bound. No one's improved this for 35 years. So try to prove it by 1. Do something. Start the hole in the dam. Okay, now going on to what could be true for partitions of the plane. Now, if you allow an arbitrary finite number of colors. Before, 7 colors stop this, 4 colors do or don't, so forth. Now I'll give you just the plane, but I'll give you as many colors as you like. Well, here's a typical kind of result. For every number of colors, there's some least integer t of R. No matter how you partition just the lattice points into R color classes, one of these color classes contains the vertices of a triangle whose area is exactly TR. So given R like 100, I'll produce an integer, depending on 100. No matter how you 100 color all the integer points, you can't avoid 3 vertices with a triangle with exactly that area in the same color. How large is this? Well, you can show that it's at least exponential, half times the least common multiple of the first R integers. So that's about e to the R. The best known upper bound grows pretty fast. Already the van der Waarden function is, for R colors, is just the least integer, so that any R coloring in the first W integers, you get a k-term progression. We've seen the case 2. And T of 3, for example, from the construction, is less than 725,000 times the next number, factorial, times the van der Waarden function of this factorial for 3 colors, factorial. That's the upper bound that comes from the proof. Again, the proof is highly recursive, as you might imagine. The actual value is 3. Yeah, that's the value is 3. But so again, you always get these embarrassing gaps between what's true and what's the truth? I don't know. Probably the lower bound is, the smaller range is probably going to be closer. What if you allow infinitely many colors? So you got the plane, I'm just going to allow you an infinite number of colors. Now, is there anything you could guarantee? Well, Thermokunin says if you assume the continuum hypothesis, you can partition all the points into countably many sets, none of which contains the vertices of a triangle with rational area. Well, now you're kind of losing the combinatorial flavor, but you know, this is a Ramsey theorem. In fact, Erdős and Comyat show that the existence of a partition of the points in the plane in countably many sets, none of which contains the vertices of a right triangle, is equivalent to the continuum hypothesis. So again, you start, as Erdős liked to say, you know, the undecidability raises its ugly head in a lot of these questions. You either have to know what axioms you're dealing with. So maybe we'll leave this infinite stuff. Here are some set theorists. I just, this is Stan Ulam, looking kind of funny. This is Dan Malden, who's a set theorist down in Texas. Some of you may know. This is his son, who's now 27. Erdős loved to hold these epsilons, as he called them. Now, one more topic before we wind up here. Edge Ramsey configurations. Same idea, except now you're not going to color the points, you're going to color line segments in Euclidean space. So if you have a finite configuration of line segments in K space, you'll say it's edge Ramsey. If no matter how many colors, there's a dimension, so that no matter how you R-color the line segments in Euclidean n space, there's a monochromatic copy of your finite set L. Okay, so what's true there? What do we know? Well, not as much. From this, in fact, this was a series of 3 papers. It's Erdős, Graham, Montgomery, Rothschild, Spencer, and Strauss. If you have an edge Ramsey set, then all the edges must have the same length. Furthermore, the endpoints of the edges must lie on 2 spheres. So it's a little bit like the one sphere. Instead of being spherical, the endpoints must lie on 2 spheres. And if the endpoints do not lie on a sphere, and the graph formed by this is not bipartite, then it's not edge Ramsey. So this rules out certain configurations, but there's a big gap between these 2 results. And fairly recently, Cantwell showed the edge set of an n cube is edge Ramsey. The regular n-gon is not edge Ramsey if it's 5 or bigger than 6. 6 is not known. Regular hexagon, can't decide. That's an open question. Characterize edge Ramsey configurations. There's no plausible conjecture. Nobody has a conjecture. I'll tell you for point Ramsey what the conjecture is in a minute. We recall sphere Ramsey implies spherical implies rectangular. And certainly you can't go back this way. There are rectangular sets that are not spherical. But what about the other direction? Does Ramsey imply sphere Ramsey? Spherical imply Ramsey? 1,000. Prove or disprove? You know, on the Clay Mathematics Institute offered $1 million for 7 problems. One of them looks, you know, they better get their check out. At least the Poincare conjecture looked like it's looking pretty good, actually. But the question is, suppose you had a good idea on Riemann. Would you share it? I don't know. You know, you might say, well, let me think about it another few years. Let me close with now 3 easier problems. What are the unit sphere Ramsey configurations? Well, I don't know if that's easy or not. Here's a $50 conjecture. I think it should be true. For any set of 3 points, any triangle, there's some 3 coloring of the plane that does not have those 3 vertices in one color. So you can always stop any particular triangle with 3 colors. In fact, kind of stronger, any 2 coloring of the plane contains a monochromatic copy of every triangle except possibly a single equilateral triangle. If you wanted to stop an equilateral triangle of side 1, how would you do it? It's kind of only one way known how to do it, with 2 colors. Take strips whose width is square root of 3 over 2, which is the altitude of the triangle, make it closed on the bottom and open on the top. Just do that. The triangle won't quite fit in there, and it's not big enough to cross. And that's so the question. So it seems that no matter how you 2-color all the points in the plane, if you do stop a triangle, it has to be equilateral. You can only stop a single one. Everything else occurs. Any 4-point subset of a circle is Ramsey. Certainly spherical. And you know, the Krish result doesn't apply there. Every spherical set is Ramsey. It seems, the conjecture is, these are the Ramsey sets in the plane, the sets that are spherical. Here's Erdős, and I might mention that there's a new volume. Gunther Ziegler just told me that the third edition, proofs from the book, is how long do we have?